All right, welcome to the Explainer. Today, we're diving deep into a question that's, well, it's at the absolute core of what it means to be a great developer. See, it's not just about getting your code to work right now, it's about building something that can actually last, something that can stand the test of time. You know this feeling, right? If you've ever written a line of code, you've been here. Getting that program to finally run, to do what it's supposed to do, that's kind of the easy part. The hard part, the thing that really separates the pros from the beginners, is making that code last. So, how do you build software that can actually evolve and adapt over years, without just completely falling apart into a tangled mess? Okay, so to really get this, let's follow a story. Picture this, there's a developer, and they're working on a project called the Nimbus 1.0. It's just a simple little weather station. And you know what? At the beginning, everything is awesome. The code is clean, it works like a charm, the client's happy. What could go wrong? So the design at the start, it's dead simple. You've got a scheduler, right? It just pokes the sensors every so often to get the latest temperature and pressure, and then it shoves that data directly onto a monitoring screen. And hey, for what they needed at the time, it was perfect. It worked. But here's the kicker, and this is so important. A design that's perfect for today can become an absolute prison for tomorrow.
And there it is, the dreaded meeting. Management announces the Nimbus 2.0. It's going to be faster, cheaper, better. You know the drill. But there's one tiny problem. It uses completely different hardware. We're talking a new processor, all new sensors, a different clock, the whole shebang. For our developer, this is a total nightmare. Why? Because all that simple, beautiful code is now hardwired to a bunch of hardware that's about to be thrown in the trash.
And this brings us to our first big villain of bad software design, rigidity. You know this one. It's when your code is basically a house of cards. You try to change one little thing over here, and because everything is so tangled together, it creates this domino effect. Suddenly you have to make changes in 10 other places. What should have been a simple update turns into this huge, scary, high-stakes project. And right alongside rigidity, you always find its evil twin, fragility. Oh man, every developer knows this terror. You make a change, a totally reasonable change in one spot, and then, for no reason you can see, something completely unrelated breaks. The system is just so brittle, so fragile, that you're scared to touch anything. It really is like walking through a minefield every time you have to deploy. So this is the big question, right? For our developer and for us. How do we get out of this nightmare? How do you escape this cycle of brittle, unchangeable code? How do you actually build software that, get this, welcomes change instead of being terrified of it? Well, the answer isn't about working late or just trying harder. It's about working smarter. It's about using some really powerful foundational ideas called design principles. All right, let's look at the first key to unlocking this puzzle. And honestly, this might be the most important one of all. It's called the open-closed principle. This idea is an absolute game changer for building code that can actually grow and adapt without shattering into a million pieces. So this principle, which comes from a guy named Bertrand Meyer, it sounds like a complete paradox at first. Software entities should be open for extension, but closed for modification. Wait, what? Open but closed? What does that even mean? Well, it's actually simpler than it sounds. It means you should be able to add brand new features to your system without ever touching the old, stable working code. Think about it like a power strip. A power strip is a perfect real-world example. It is absolutely closed for modification. You don't call an electrician to rewire your house just because you bought a new phone charger, right? Of course not. But it's completely open for extension. You can plug in a new lamp, a TV, whatever. Great software design is all about creating those same kinds of stable outlets for future features. Okay, so how do we actually build these outlets in our code? How do we make this happen? The answer is in another killer principle. This is the one that lets us build basically firewalls inside our code, walls that protect the important, stable stuff from all the messy, unpredictable details. And this one is called the Dependency Inversion Principle, or DIP, and it literally flips our normal way of thinking completely on its head. See, normally we think of our main application logic depending directly on the nitty-gritty details, like a specific sensor driver. This principle says, nope, do the opposite. Both your high-level logic and your low-level details should depend on some kind of abstract agreement or an interface that sits right there in the middle. Let's go back to our electrical analogy. Think about that outlet in your wall. Your lamp, that's your high-level thing, right? It doesn't know or care if the electricity is coming from a nuclear power plant or a solar farm. It doesn't care about any of those details. All it cares about is the standard plug, the two prongs. That is the abstraction. It's a stable contract that totally separates the lamp from the insane complexity of the power grid.
And you can see the magic of it right here. Before, you have this arrow of dependency pointing straight down. Your high-level logic is just stuck, chained to the low-level details. But after we apply this principle, look what happens. We invert the arrow. The high-level module points to the interface, and now the low-level module also points up to that same interface. That interface in the middle, that's our buffer. That's our firewall.
Okay, so we've got these incredible principles: open-closed, dependency inversion. They're like the laws of physics for good design. But how do you actually use them? How do you write the code? Well, that is where design patterns come into play. Think of them as the superpowers our developer needs. They're the proven, practical recipes for solving these exact kinds of problems.
So our developer gets to work and comes up with a two-step plan. Step 1, use something called the observer pattern to break the connection between the sensors and the screen. Step 2, use the bridge pattern to build a wall between the main application and that messy, ever-changing hardware.
Let's talk about the observer pattern first. It's so clever. The temperature sensor no longer has any idea that the monitoring screen even exists. Instead, it just sort of shouts into the void, "Hey everyone, the temperature just changed." And now any other part of the system that cares about the temperature, whether it's the screen, a database logger, an email alert, or whatever, it can just subscribe to those announcements. The sensor is now totally free from knowing who's listening.
Then you've got the bridge pattern. This one goes right after that huge hardware problem. What it does is create this super stable, clean API, a contract that the main application can always rely on. Now behind this bridge, you can plug in the code that talks to the old Nimbus 1.0 hardware, and later, you just unplug that and plug in the new code for the Nimbus 2.0 hardware. And the best part? You don't have to change one single line of your main application code. That is our firewall, right there, in action.
And just like that, crisis averted. Our hero developer has taken this codebase from a rigid, fragile nightmare and totally transformed it into something flexible, something resilient. So now, when that new Nimbus 2.0 hardware finally shows up, adding it isn't some soul-crushing rewrite. No, it's just a simple, manageable task, writing a new little plugin that fits right behind that stable bridge interface.
So what's the big lesson here? What's the takeaway? Look, good design is never about achieving some kind of mythical perfection. It's about one thing: anticipating change. The whole goal is to build a system using these stable abstractions and decoupled parts so they can evolve on their own. It's really about making sure every piece of your code has one and only one clear job to do.
So here's a final thought for you. The next time you're using an app on your phone and it gets a big update with some cool new feature, just stop and think for a second about what had to happen behind the scenes. Was that change possible? Was it easy because that app was built on a solid foundation of stone? Or was it a complete nightmare for the developers because the whole thing was built on a foundation of sand? It's a question that tells you everything about the quality of the software we use every day. Thanks for joining us on The Explainer.